Sir, you can start, sir.
Can you hear me, madam? Can you hear me?
Yes, sir. Yes, sir. Yes.
We welcome on this day for this webinar Dr. Sharvil Alex Faros. He's very kind enough for having accepted our invitation to come on this webinar. We are extremely thankful to him on behalf of QCrete India Private Limited. And this webinar is being conducted on in association with ICA Kochi. And just a brief introduction to Dr. Sharvil, sir. Dr. Sharvil Alex Faros is founder of IRM, which means Infrastructure Risk Management Company, based in Mumbai. He began his civil engineering journey from VJTI, Mumbai, earning his BTech degree, then Masters in Structural Engineering, SPCE, Mumbai. Later on, he did PhD in Structural Engineering from IIT Mumbai. During his PhD, Dr. Sharvil interviewed various civil asset owners and understood their challenges specifically regarding the life cycle challenges of such structures, which is very, very important and very, I can say, niche area. Though through his insight, his PhD focused on creating an applicable technology for evaluating remaining useful life of civil structures, which help clients with decision making on longevity and rehabilitation. Dr. Sharvil's company, where he is founder, is based on this technology, which I understand from Dr. Sharvil that it is a proprietary and copyrighted unique technology. His company IRM is helping clients to massively reduce the risks and minimize the operation and maintenance cost of their civil structures and extending their service life. These assets include commercial buildings, bridges, refinery chimneys, and ports, and more. The company has grown 7 times since its inception. Dr. Sharvil, at a very young age, I can say, has achieved very big things, and it is very difficult, I can say, to just capture on a piece of paper or in 10 minutes or 5 minutes. He has done extremely good work in the field of rehabilitation and analysis, including his assignments abroad. With this short introduction, I welcome Dr. Sharvil sir once again. And once again, I thank him for accepting our invitation on this platform. On behalf of QCrete India as well as ICA Kochi chapter, we welcome you, sir. Please, the floor is yours now. Thank you.
Thank you, Kaushik sir, for this introduction. And also thank you to Lata Shri ma'am for this organizing this webinar. Okay. Before I begin my presentation, okay, I am showing you one context slide before I begin my presentation. Okay. So you might be knowing that in our country, all major cities are developing metro networks, metro railway viaducts throughout their cities, right? And most of them, if you observe, they will have in the tender document life of 120 years. Okay. So by 120 years, have you ever thought, like, what does it mean to have a life of 120 years? Like, what does it mean? Okay. So these are some of the challenges which are existing in the market today. Like, people are struggling to understand what do they mean by 120 years. Okay. On the other hand, if we there was a survey which was conducted in 2017. They surveyed all the bridges of our country, and they found that the average design life of all of these bridges came out to be around 34.5 years only. We are talking about 120 years, but see, presently the average age is just 34 years. And they were thought to be at that time, like, these are old bridges, and they were thought to be designed for a life of 75 years. So you can see that there is a deficiency of 56% in the total life, right? And all these old bridges, they have become structurally deficient, and they require a lot of cost, a lot of money for doing the repair and rehabilitation. And in one statistics, it was found that the cost of repair and rehabilitation is more than 50% of the construction cost of the original project. Okay. So then people also thought, like, why this is happening? If we said we are designing for 75 years, 100 years, why so the life is so short? Okay. So this then some research was conducted, and two eminent engineers, Marsh and Frankopol, okay, here, they found that the reason for this, they found that the bridges are having so short life because when we were designing those bridges, the effect of degradation or effect of corrosion, okay, corrosion you may be knowing that it is one of the major factors of degradation. So we did not account into the design the effect of degradation or corrosion. And therefore, these kinds of deterioration leads to the interruption, or like we have to stop the services, we have to do the repair and rehabilitation. Okay. So just imagine if we are making our metro railways for 120 years and they get deteriorated. Will it do justice to the billions of rupees that we are spending in constructing this metro? I think one of the metro railway, the cost has gone up to like 10,000 crores or something. So much money we are spending, and if the bridges or the viaducts will not last for a very long time, okay, so are we really doing good engineering? Okay, so that was the main motivation. And so this with this problem, we thought that why not solve this challenge for the industry? Okay. So we through my research, okay, I did my research at IIT Bombay, and this technology we developed, it is called M.F.L design, or major maintenance free life design. So this is a proprietary technology which we have developed, okay, and only provided through our company. Okay. So the rest of this presentation I will be showing to you how this analysis of deterioration is done, and how the design is done so that your bridge or your viaduct can have a tangible life or a repair free life of 120 years. Okay, so with this in context, you know why this technology is important for the metro projects, right? And so we did a project in Mauritius. That was our first international projects we did in through our company. Okay, and it was the first time where this technology got implemented. Okay, so now I won't be presenting to you exactly the details of Mauritius Metro here in this presentation, but how the experience from Mauritius Metro can be implemented for our projects in our country. That is going to be the focus of the presentation. Okay, and just keep in mind that we are not covering in this presentation, I am not covering all the aspects of deterioration, but I'll just be focusing on the aspect of corrosion, because that is the probably the most major factor which causes degradation of the structures. Okay, so this is the Mauritius Metro. So as you can see, okay, this metro line passes through a coastal area, which is a marine environment. It also passes through an industrial belt in the country, which means it is also exposed to industrial attacks. It is, as you can see, it is also exposed to the marine attacks, and also the part substructure of the bridge or the viaduct is also subjected to attacks from the ground. So all of these effects have to be considered for this kind of projects. Okay, and that with this in context, I will be showing to you how we can implement similar projects in our country also. Okay, so just it is required a clarification that there is a difference between a structural design of a viaduct and an M.F.L design. Okay, so M.F.L is major maintenance free life design. That is the short form M.F.L. Okay, this is a proprietary technology that we have. So what is the difference between a structural design and M.F.L design? Okay, so you are aware about structural design. Okay, it includes designing the viaduct for the external loads. Let's say the train load which is there, it causes bending moment, shear forces, axial loads in the viaduct. Okay, so designing or sectional designing the bridge or viaduct for these external loads is known as the structural design, right? So as you can see in this figure below, okay, that this vertical arrow which I have shown here, this is known as the structural design. So let's say you design uh, the viaduct, okay, or a column, let's say, for a load carrying capacity of 100 kilonewtons, right? So that is known as the structural design. But if you see this thick red line, that is called the M.F.L design, which means how do you ensure that your structural capacity is maintained or is sustained or for a given service life of 100 or more years. Okay, so M.F.L design focuses on sustaining the structural capacity of your viaduct for the design service life of 100 years, so that it is safe and it is above the acceptable level of performance. Okay, so this is the difference between a structural design and an M.F.L design. Okay, so now we can go deep dive into the presentation. Okay, so whenever our agencies are there which are constructing like Bangalore Metro, Chennai Metro, Mumbai Metro, various metros agencies are there, and they want to construct a new metro project. Okay, so before constructing, there is always a pre-construction stage, and during this stage, okay, we the consultants or the contractors usually have a discussion with the client about their requirement. Okay, and then once these requirements are clarified, then we move on step by step. Okay, so there are, as you can see here, this presentation is divided into 5 parts, and one by one we'll go into each stage of this M.F.L design. Okay, so let's say the owner or the metro agency is looking to construct a new viaduct. Okay, so there would be a feasibility study will be first conducted, then the engineering report will be prepared, then the contractor will be appointed. Okay, but in order to ensure what are the exact requirements of the client, the consultants should always have one-to-one discussion with the owner. Okay, and through my interaction with various agencies, metro agencies, okay, what I could understand what are their top five requirements is that they would always want to have the bridge or the viaducts to last for 120 years from the day of construction. Okay, as I told you, it is people are struggling to understand what do they mean by 120 years. Okay, so in order to overcome this struggle, okay, they are also looking to have engineering calculations, okay, which will prove to them or which will demonstrate to them how this viaduct will achieve a life of 120 years. Okay, and once you have demonstrated to them what would be the warranty, how do you show to them that yes, based on this analysis or this calculation, we are giving you a warranty which will ensure that it will last for 120 years. And one question also asked frequently by the asset owners or metro agencies is that, okay, so presently we are not doing M.F.L design. Okay, then what is the life, what is the useful life of the present design that we have? Okay, so generally you know that there would be a preliminary structural design of the viaducts will be prepared. Okay, so of this preliminary design, they want to know what is the life that would be achieved if we do not do a M.F.L design. Okay, and finally, what is the remaining useful life of the bridge, and can we do something to monitor this life? Okay, so these are all the 5 most important points which I find are being asked by the metro agencies to the consultant. Okay, so I would be showing to you how each of these 5 points can be answered, so that you can also develop and use the M.F.L design for your own projects. Okay, okay, so as I told you that first we need to have a discussion with the asset owner or the metro agency that what is the design life. Okay, how do we define a design life? So I go back to the IRC guidelines. IRC 112, you are aware that this is used for bridge design. Okay, now in this code, a beautiful definition of design service life is there given. Okay, so I'll read out to you what it says, that what is the design life? It is the period for which a structure or part of it is to be used for its intended purpose with anticipated maintenance, but without necessity of major repairs. Okay, so if you will focus here, it says that the bridges should be without necessity of major repairs. There should be no major repairs throughout the design service life, throughout its full service life. Okay, and if we see what the IRC code says, should be the life 100 years or more. Okay, so when we combine these two, what we understand is that all the bridges that we are should be making, they should remain free of any major repairs for 400 years. Okay, and incidentally, similar definition is also given in Eurocode, which the Mauritius Metro was using for their design of bridges. Okay, so in the Mauritius also they had the definition which said that it should be free of major repair. So the metro agency in Mauritius, they stuck to this definition. They say, see that what they said is, as per this definition, okay, our bridges should be free of any repairs for the full 100 years. And that is what they stuck with. So that is why it is very important to sit with the client first, talk with the client and understand what are their requirements. So now we got to understand that the owner wants to have a major repair free life of 100 or more years. Okay, so the next step would be what to identify what are the causes which could lead to deterioration. Okay, what could lead to the requirement of repairs. Okay, so you know that corrosion is a major aspect. It could be either chloride induced corrosion, which is in marine areas, and carbonation induced corrosion, which could be in highly industrialized areas. Okay. There are other aspects which are like loss of concrete strength over time with each passing year. The concrete will initially it will gain strength, but over time with each passing year it will lose strength. And many of these viaducts, they are like pre-stressed in nature. So that loss, there would be also loss of pre-stress which would be taking place. Okay, but for the sake of this presentation, I will be not covering all of this. I'll be only focusing on the chloride induced corrosion, okay, which will affect your reinforcement. Okay, because given the limited amount of time that I have, it is not possible to cover everything. Okay, but by covering this corrosion effect, you will get a fair idea what this M.F.L design is all about. Okay. Okay, so now let us define. We have identified that corrosion because of chlorides is a factor which will degrade my bridge. Okay, and our objective was that it should be major repair free of major repair. There should be no requirement of major repair throughout its service life. Okay, so take a look at this figure at the bottom. It shows how the chloride induced corrosion takes place in your structure. Okay, so initially you know that chlorides start penetrating through the concrete. Okay, so this is the initial stage which is known as corrosion initiation stage, during which the chlorides from outside the concrete starts penetrating and try to reach to the reinforcement level. Once they reach the reinforcement, okay, then the corrosion will start, rust will start to form, and then this like cracking will take place of the concrete. Okay, this is known as the propagation stage. And you know that whenever there are cracks to the structure or to your viaduct, okay, or your any kind of structure, whenever there are cracks, we go and do the repair. So if we want to have a repair free life, then we should prevent the occurrence of these cracks. Okay, so just imagine if we can limit the ingress of chlorides to the reinforcement, okay, so that they reach the reinforcement only at the end of service life, then we can achieve a repair free life, right? Just imagine chlorides are penetrating the concrete, and if we design the concrete or the structure in such a way that the chlorides will reach the reinforcement only at the end of the service life. It means that the corrosion or the repair will be required only after the end of service life. So we have achieved our objective that our design service life of 100 years should be free of repairs. Okay. Now, depending upon the shape of your structural member, so viaduct can have piers, it can have the U girder, it could have I girders which are there, and they could have various shapes. So the deterioration or the chloride attack which is taking place will depend upon the geometry of your structural member. So if it is like a thin wall member, then the chlorides are like you can see the perpendicular diffusion will take place. If it is a circular pier, then radial diffusion of chlorides will take place. If it is a square pier, then the diffusion will be taking place in a two-dimensional manner. And if it is a complicated geometry like the pier head, okay, then it is a three-dimensional attack of the chlorides. So the shape also affects your deterioration factor. Okay, so each shape will have its own unique deterioration model or deterioration performance. Okay, so that you have to keep in mind. Now I am taking you to a micro picture. Okay, so in the previous slide I talked about the macro picture, how the chlorides start penetrating from outside. Okay, now I am taking you to a micro picture. Okay, this is a section of your concrete. This is your external concrete surface. This is your reinforcement. Okay, CS is the total amount of chlorides that are penetrating or that are attacking from outside. This red line indicates the chloride attenuation within the concrete, or how the chlorides are penetrating. It indicates that, so it is a concentration function or attenuation function. Okay, this T is the external temperature. Okay, and this D is the diffusion property of the concrete. Okay, you may have heard in recent times about global warming, climate change, right? So this climate change will affect your temperature. So temperature will rise with time, and if you consider 100 years or 120 years, the temperature is definitely going to rise from whatever we are facing today. Okay, and this T temperature will affect your diffusion properties of the concrete. So this D, what it does is the rate at which the chlorides can penetrate through concrete. It indicates that factor. So higher the temperature, faster will be the penetration of chlorides through the concrete. Okay, so you can understand that climate change will really affect your corrosion aspect of the concrete. Okay, so just 1 degree rise in temperature can cause around 32% rise in the corrosion activity. Okay, this capital X indicates your concrete cover. This CTH indicates the corrosion resistance of the reinforcement. Okay, so we have the so below you can see that we have the chloride attenuation function. Okay, which will again depend upon the geometry of the structural member, and we have the chloride resistance of the rebar, which is indicated by CTH. Okay, and this small t indicates the time factor. So that is where we will be plugging in our life of 120 years or 100 years. Okay, so before we start with the project, okay, we need to first decide what are the input parameters which are required. See, as you would expect that this is an analysis. First we have to do analysis and then we have to do design. So for analysis, we first need to understand what are the external loads or deterioration loads. So chloride, I am calling it as a deterioration load which is acting on your structure. See, it is necessary that you identify what is the magnitude of this chloride load. Okay, just like whenever you are designing your bridge or viaduct for a axle load of train like 28 ton, so that is a load which is coming on your viaduct. Similarly, this deterioration load or chloride load, we need to quantify what is the amount of chlorides that are attacking your structure. So that can be identified in various format, and one of the format I am showing here. Okay. So if there is an already decided concrete which the client has defined that okay, we are going to use this concrete. So based on the information that we have of the cement, fly ash, okay, annual temperature exposure, amount of chlorides in the salinity of the sea, the type of exposure, okay, is it atmospheric chlorides are attacking, is it submerged in saline water, is it tidal zone, and so on. So depending upon each kind of attacks which are taking place on the structure, they will have different values of this CS. Okay. So what we are doing, we have developed algorithm, machine learning algorithm. Okay, this is our again proprietary software that we have developed. Once we feed or input these parameters into our software, machine learning software, they will provide to us how these chloride loads will vary with time for the given site condition. Okay, so this data, okay, so we have our original machine learning model which is trained through data that is available in the literature. Okay, lot of experiments also have been conducted, and this data is also collected from there also. Okay. So once we feed all these inputs which are indicated on the left hand side, so our software will tell us what is the amount of chloride loads that will be acting on my viaduct over time. Okay. So we have calculated what is the load which is acting on the bridge. Next step is also to identify what is the diffusion properties of the existing concrete mix that the client is suggesting. Okay. So again, this is obtained. So we have created one database for the given concrete mix. What is its value of the diffusion? Okay. And this is indicated by the unit meter square per year. Okay. So this is available to us. So once we know the concrete mix, we can easily associate what is the value of diffusion that this particular concrete is going to have. Next, we come to the climate change, which I told you earlier. So IPCC is a organization which has created various climate change scenarios. Okay, and as you would imagine, Mauritius being a tropical country, the effect of global warming and effect of climate change is very severe for them. Okay. Similarly, this climate change model can also be adopted for our countries. Okay. So we created one model for Mauritius. Similar also we can create for our projects which are there in our cities. Okay. So as you can see that the temperature trend is kind of rising in nature. So this has to be included in our analysis as well. And then finally we also come to the CTH parameter, okay, which indicates the resistance of the reinforcement towards the corrosion. Okay. Again, it will have certain inputs which we need to provide to our machine learning algorithm, and it will tell me what is the value of CTH for that particular site condition. Okay. So now, as you can see, we have collected all the necessary input data that we should do before we do the analysis. Okay. So once we have collected all the data, now we go to the next step, which is called the actual designing and analysis using the M.F.L design. Okay. So this software that we have, it is called M.F.L 100 Plus. Okay, this is our own software that we use for such projects. Okay. So now to show you an example how you should do the design and analysis of this project, let us consider one pier of this viaduct. Okay, so this is a circular pier which I have shown you. Okay, and let us consider, so as you can see, there would be two conditions. One is the part of the pier which is underground and the part which is above the ground. So above ground will be facing airborne chlorides which are attacking it, and the part which is underground, they will be subjected to chlorides which are attacking through the salinity of that soil or salinity of the underground water. Okay, So let us take the example of underground submerged condition, underground condition. Okay. So this image, as you can see, of the circular pier, the reinforcement position as shown, and the chlorides are attacking it radially. Okay. And as you can see here, this is the ingress function, or how the chlorides penetrate through the concrete. So this is a deterioration function for this design. Okay. Where, so in this relationship, so this capital C here indicates the chloride concentration inside the structure or inside the component. Your capital DT indicates the diffusion, which I have shown you previously, and how it changes with time. This small r indicates the radius, because this is a circular pier, it will have a radius. So small r indicates the radius, and small t indicates the time function. Okay, and this is a partial differential equation, okay, that we are going to use in our design. Okay, so now let us create the design equation. Okay, so in this design equation, we need to first create a limit state. So by limit state, you are very well aware about limit state of shear, limit state of flexure, okay, that you are aware of. So similarly, we also create one limit state for corrosion. Okay, as you can see here, this limit state is G as a time dependent limit state, and then we create it equal to CTH, which is the resistance of your reinforcement, minus the chloride attenuation. Okay, and chloride attenuation function, which is there, is obtained by solving the previous differential equation and giving all the inputs which we collected in the first stage. Okay, so this is our design equation, and it is solved at the time when, let's say, time t equals to 100 years. That is the design life that we want. It could also be 120 years. Okay, so the design solution is that the probability of this limit state at the age of 100 years, or let's say 120 years, should be less than the target probability of failure. Okay, so it means that this, again, if you are interested, I will also tell you a bit detail about this. Okay, so as you can see here, so CTH is the resistance, and when the external chlorides become equal to CTH, it indicates that the limit state is 0, okay, which is a failure, and at that point corrosion will start. So we want to limit that limit state not beyond equal to 0, or it should not become negative. Okay, so therefore this limit state is limited here, okay, up to the target probability. Okay, and then once we solve this equation or solve this design problem, okay, we get output as this. Okay, so based, as you can see here, these are the parameters CS, X, D, T, capital T, small t, CTH. This can also act as a design variables in our parameters. Okay, so there are total 5 design outcomes or 5 design parameters which you could modify or you could use to do the design. Okay, so I'll just list out here. One is the concrete type. Okay, so concrete type will depend upon the diffusion of the property. Then the second is the cover size which you can use. Third parameter is called the rebar type. So each rebar, as you know, one is carbon steel, there could be stainless steel, galvanized steel. Each will have a different value of CTH. Okay, so each rebar will have a different resistance value. And then type of inhibitor, what kind of, how much inhibitor to put, what kind of inhibitor to put. And finally the surface coating, is there a surface coating should be implemented or not. Okay, so these are all the parameters which we can manipulate or modify for our design. Okay, so this just figure on the left hand side, you can see it shows how the mechanism takes place. External chlorides are penetrating, and we want to have a design such that it should tell me what should be the geometry, what is the best geometry which I should have for my viaduct, what should be the best concrete which should I have, what should be the best size of cover, what should be the type of steel reinforcement should I be using, should I be using any admixtures or should I be using any coating. That these are the outcomes which I should be ideally getting from my design, right? So once you have done this this M.F.L analysis and design, okay, now it will provide to you the specification for execution. So it will tell all the specifications which you should provide to the contractor. And let us take a look at what are the specifications you can provide to the contractor. Okay. So the first is the type of concrete. Okay. So MX is the grade of concrete in terms of strength, and D is the DY is the terms of diffusion. So it will of course depend upon the capital D that you have or the diffusive property. So we tell through the contractor, your concrete should have a diffusion value of so and so, okay, and it should not exceed this particular value. Second, we also specify to the contractor what should be the size of cover that should be the defined, and along with its tolerance. Okay. Then we also say what is the type of reinforcement steel to be used, which will depend upon the value of CTH, the type of inhibitor that you should add, or type of other admixtures that you can add to your concrete, which will also depend on the CTH. Okay. And finally, also the coating material. If by manipulating other parameters still your service life is not getting satisfied, then we should think about adding coating material, so that the thickness of the coating and the material to be used will depend upon my design parameters D, X, and CTH. And finally, the geometry of the member. So we can also tell to the contractor that you modify your present geometry to this geometry so that it faces less amount of attacks. Okay. So now, as you can see here, all these specifications that we are producing, okay, for the construction, these are based on engineering analysis, calculations, and as an outcome of this calculation, we are providing the specification. So it is not dependent on the prescriptive provisions or any suggestions made by some random value that we have to provide. Okay, you put this much amount of cover, you use this concrete, you use this kind of inhibitor. Okay. So this design is not based on random suggestions by any expert, but these specifications are based on the engineering analysis and calculations, and based on this calculation we are providing you the results. Okay. And after this result, the warranty will look like this. Okay. It will show you the deterioration profile. This thick blue line indicates your limit state degradation with time. Okay. And it will cross your threshold value, which is the threshold probability, or PT, which I showed you in the previous slide. Okay, let me go back there. This PT, okay, that is the threshold value, and it will cross my threshold value only after my service life is complete. Okay, so this is also a visual representation of the calculations, which can be showed as a design warranty for this kind of design. Okay, so far what we have covered is all the office work that we have done. So we have done all the office work through the calculations and through providing the specifications to the contractor. Now the job comes to the field work. Whatever specification we are giving to the contractor, is the work being executed as per those specifications or not? We need to check it. Okay, so now we'll do that stage here. Okay, so there is a test called field migration test, which is very important for chloride induced corrosion. Okay, so while the concrete is being poured at the site, we collect certain we cast certain concrete cylinders. Okay, as you can see here. Okay, and they could be based on minimum sampling frequency as suggested by our Indian standards. Okay, and we conduct the rapid migration test for these kind of concrete samples. Okay, and we store these values. But also, in addition to this migration test that we do, we also do a resistivity test, okay, on these concrete samples. As you can see here, this one photograph we have taken, you can show here. So see that this resistance test is being conducted on this concrete sample, and for the corresponding resistance of that sample of concrete and its corresponding diffusion value, which we tested previously, we get some value, some graph like this. Okay. So why we did this resistance test, that I will tell you in the coming slides. Okay. But for now, just keep in mind that we have also done this resistance test. Okay. Then if the client demands, we could also do a long-term monitoring of the chloride ingress into our concrete structures, okay, through this kind of monitoring system. And this can provide us the remaining useful life or the lifetime of the viaduct in a real time. Okay. So this can be provided if the client wishes, or if the client wants to know really what is the performance of your viaduct with each passing year. Okay. So in that case, it is really helpful to the client to have a monitoring or to track the performance of their viaduct. Okay. So this was during the construction stage. Okay. Now we come to the part when the construction is almost done and finished. Okay. So one of the tests which we could easily do is measuring the cover. Okay. As you understand that the chlorides are penetrating through the concrete cover. So let us quantify also what is the amount of cover which the contractor has casted. Okay. So this is one of the measurements I am showing you. Okay. So here, in what way you should do the measurement. Okay, so this is one of the wall face which you can see here, and we are making a grid on this concrete surface, and at the intersection, at the grid points, we are doing the measurement of the concrete cover. Okay. So the table below, you can see this is the data that has been collected. Okay. And the figure on the right hand side, you can see the distribution, frequency distribution or probability distribution of the data that we have collected. So it tells you, when let's say you specified a concrete cover of 75 mm, but when we did the actual measurement, we found that the concrete cover ranges from 60 mm to 85 mm. Okay, so there is a distribution of values. Okay. This is expected because it is since it is a huge structure, there is bound to be certain slight variations in the specifications. But again, it is important that we note down this data, okay, once the construction is completed. Okay, and why we are doing that, again I'll tell you. Okay, and now again, next step, we should also do the resistivity measurements on the finished concrete surface. You remember this figure from the previous slide, which I told you I'll be explaining to you later. Okay, so now this is the point where I'll tell you why we did this. Okay, so we created a relationship between the concrete resistivity value and the diffusion value. Okay, so when we do the resistance test on the finished concrete surface, we can indirectly get what was its diffusion value. Okay, so similarly, we create a grid system and measure at each location what is the resistivity of the concrete surface, and we get a plot like this. On the top left, top right, as you can see, we have a probability distribution of the diffusion values. Okay. So now is an important stage. This is an important stage to check the acceptability of the work which the contractor has done. Okay. So the tender specified that the bridge or the viaduct should have a life of 120 years. So it means that if the contractor has done a good job, the bridge should demonstrate to me through my analysis that it satisfies 120 years or more. But if the contractor has not done a good job, then the life prediction should fall very less than 100 years. Okay. So now what we did, we collected the data during the construction stage and post construction stage, right? So these inputs we again feed to our software and evaluate the life of your viaduct. Okay, so if it is greater, if we found somehow that the contractor has an excellent job, in that case also the life we could get is, let's say, even more than 120. So in that case, you accept the project and release the payment to the contractor, and if possible, you may also reward the contractor. Okay, but if it is falls short of your 120 years, Okay, let's say it goes up to only 97 years through our analysis. Then you could ask the contractor to do the corrective measures to fulfill the balance 23 years which are left. Okay, you may even halt the contractor's payment in that case. And once the contractor has fulfilled through the balance 23 years of life, then you can release the payment. Okay, so these are some of the concepts which we learned from abroad, where we did the projects. Okay, so that is why I'm presenting to you these concepts. Okay, so now we have done all the analysis, we have completed all the project, and we have now uh, concluded the particular metro project. Okay. So now what is the takeaway for you? Okay, what do you learn, what can you learn from this technology for your own projects, right? So this is some of the takeaway which you could use for your own projects. Okay, so I have given it in a flowchart format so that it becomes very communicative to you. Okay, and it is very easily represented through this format also, right? So let us start with this goal. Okay, so the goal is we want a major maintenance free life of 100 or more years, which also means that it should be repair free for 100 years as per the code. Then we create the performance limit state which I have showed you, and through the acceptable inputs, whatever site specific inputs are there for that particular project, you input those. Then for the existing design which the client already has, okay, do a remaining life analysis of that existing bridge design. Okay, and check if it satisfies 100 years or not. If your remaining life analysis tells you that it satisfies 100 years, then you need not do the M.F.L design. Then accept the design specification and conclude the project. But if your life is found to be less than 100 years, then you go for M.F.L design and analysis, and you will produce new specification for that project. Okay, and then the pre-construction phase is concluded. Okay, now in the next stage, you need to verify if the contractor has done a good job or not. Okay, so that is the our requirement for the second stage. Then through the data that I have shown you, what we collected during the construction and post construction stage, you feed that to our software, do a remaining life analysis, and check if it satisfies 100 years or not. If it does not satisfy, okay, it means the contractor has done poor job and you reject the project, or you ask them to perform target life rehabilitation, okay, to satisfy the balance life which was not satisfying up to 100 years. Okay. If it satisfies 100 years, then yes, accept that the contractor has done a really good job and conclude the project. Okay, so these are the two takeaways which you can use for your own projects. Okay. And finally, let me conclude through the utilities. What are the utilities of M.F.L design? Like, if you design your structures with this M.F.L technology, what are the benefits and the advantage that you get? Okay. First of all, the first one is uninterrupted operation. So what is an interruption? Whenever there is requirement of repair and major rehabilitation, sometimes the bridges have to be shut down also, or partially shut down. That is an interruption. So if we are ensuring that the bridges and the viaducts are repair free, it means that we can have an uninterrupted operation. Okay. Of course, it will be repair free and deterioration resistant. Plus, as you can see that whenever you spend money on repair and rehabilitation of your structure, basically it is not a productive use of your money, right? So if you use M.F.L design, you are going to massively save upon the money that you are going to spend on repair and rehabilitation. And plus, it will give you peace of mind, because you know that my structure is deterioration resistant and nothing is going to happen to my structure. In one statistics, it was found that you can save more than 50% of the construction cost if you use this technology, because statistically it has been found through various projects. Last 30 years, it has been found that major repairs, major bridges which require repair, they have costed more than 50% of the initial construction cost. So if you use M.F.L technology, you can massively save that cost, which could be even more than 50%. Right? So what could be our deliverables? So suppose we are engaging with a client for this kind of M.F.L technology. Okay. So what are our responsibilities towards that client? Okay. So our responsibilities will be to do a deterioration analysis for the design service life and provide the design calculations, which will demonstrate to the client why we are saying this design will last for 100 years. So we provide the engineering calculations, and then the specification of the works, what should be the specification which the contractor should use. Then the QA, quality assurance, quality control specifications, which I showed you how we do the measurement during construction and post construction. Plus we also prepare tender documents for including this kind of projects. So we have our own tender specifications, which also was inspired through the Mauritius metro project, okay, which we can share with the client, and providing life cycle monitoring system for the project, because that will give you massive confidence in terms of tracking the performance of your structure. Right? So with this, I conclude my presentation. Please feel free to ask any questions from this presentation. Thank you so much. Thank you.
Thank you so much, sir. The session was very interesting and informative. Next, we'll move on to the question and answer session. The first question is, hello, sir. Am I audible?
Yes. Yes, ma'am. Yes, ma'am.
Yeah. Okay. First question. The diffusion coefficient is not constant value. It varies with time due to the pozzolanic reaction of the supplementary cementitious materials. Hence, may I know at what age of concrete you are considering the D value? It is asked by Dr. B. Kameshwar Rao.
So this, Dr. Kameshwar Rao, as you said, this is a time varying factor. And let me go back to my equations which I have shown here. So in this relationship, at the bottom, you can see this equation. So this D is a function of time, right? So we consider this diffusion to be a time varying factor, okay, for our analysis. Generally, this kind of relationships is time varying up to a certain time because of these pozzolanic reactions which are taking place, and after that certain period we assume that they to be constant. So to give you a value, if I consider OPC, then generally it is around 50 to 60 years. If I consider fly ash, then it is around 30 to 35 years. So what you can understand is, if you want to simplify this DT, okay, then from the initiation of the project up to, let's say, 30 years, it is time decreasing, and then after that the decrease is very small. Okay, so this is how the time varying effect is considered. Thank you.
Thank you, sir. Next question. Rapid migration test. Is it applicable for or suitable for concrete containing metallic fibrous or conducting admixtures? It is asked by Yuvraj Singh.
Could you repeat? There was some disturbance. I could not hear properly.
Yeah, okay, sir. Rapid migration test. Is it applicable or suitable for concrete containing metallic fibrous or conducting admixtures? It was asked by Yuvraj Singh.
Okay. Okay. So we have not done this rapid migration test on the concrete which you have mentioned, Mr. Yuvraj. But what ultimately it says, what it should do, okay, is that it should demonstrate to you, this test, rapid migration test, should demonstrate to you how fast the chlorides will penetrate through your concrete. Okay, it should indicate that. But we have not done a test on the concrete which you have specified, so I do not know right now. but if we come across it, I'll let you know. Please do write to me. Our email address is there. Please write to us, and I'll send you the relevant information. Thank you so much.
Thank you, sir. Next question. Can we correlate D value and the RCPT value? It was asked by Dr. B. Kameshwar Rao.
So there is some efforts have been made to relate, but there is lot of scatter. So not RCPT is very difficult to relate because it was found lot of scatter is there. So we could not come at a uh, conclusive estimation whether RCM, which is rapid chloride migration, and RCPT can be related. But according to my experience, it is best to have RCM only, rapid chloride migration, because it can be used to have it can be used to predict and to use in our analysis and design, whereas RCM cannot be used in our analysis and design. Thank you.
Thank you, sir. Next question. The formula you have derived is based on site criteria or analysis based on IS codes. It was asked by Pawan Kumar V.
Which formula?
That he don't mention, sir.
Because there were many formulas here, so like which formula?
Yeah, okay, sir. Thank you. And next question is, you have covered effect of chloride induces corrosion. Does the M.L. 100 plus takes into account to the loss due to pre-stress or other causes leading to deterioration? It was asked by Yuvraj Singh.
So as I told you at the start, Mr. Yuvraj, as I told you at the start of the presentation, that in this presentation I am only showing you the effect of chlorides. There is like the effect of concrete strength reduction over time is also there. Carbonation is also there. Loss of pre-stress is also there. So our software, what I have shown here today, is just one module of the software. So depending upon other types of deterioration which are there, we can handle those kind of specific problems as well. Thank you.
Thank you so much, sir. Next, I will hand over this session to Engineer V.R. Kaushika sir to vote of thanks.
Good evening. Excellent presentation by Dr. Sharvil Feroz sir. We are honored with your presence in this QCrete webinar series. We look forward to have many more lectures from you in future. The subject which you have dealt today is really a kind of a completely specialty subject, and I can say in this field there are not many people who have worked in this. I can say at a young age, developing algorithms and softwares to put perspective into making this rehabilitation simpler, better, and the risk assessment and guaranteeing or warranting 100 years service life is a very, very extremely special subject, and we are thankful to you for being with us.
Thank you, sir. Thank you so much for this opportunity which you have given to me, sir.
And I'm sure
really
audience
grateful.
have gained some insights on this into this new area of research which you have done. Being with us, have more audio. Thank you. With this, we close this session today. Thank you.
Thank you, sir. Thank you so much for this opportunity, sir. Really grateful to you, sir. Thank you so much.
Thank you, sir.
conducting webinar in a very successful way. Thanks a lot.